All right, Royals, in this lesson, we're going to look at Newton's second and third laws. More importantly, we're going to do some problems that involve us to use these two laws. So you'll see that the first problem that we're going to look at has three spheres that are hanging from ropes. And we know that there is a force of gravity acting on them. And they are 21 newtons acting on sphere A, 15 newtons acting on sphere B, and 11 newtons acting on sphere C. And the first thing we're asked to do is to find or to state the free body diagrams for each of these spheres. Okay, so let's go ahead and do that. So A part, let's deal with the free body diagram of sphere A. And so if we look at sphere A, it actually has two forces acting on it. There's a force acting upwards, which I will say is the thread pulling upwards connected to the ceiling. So if we draw our box here, that's going to represent sphere A. And if we draw that first force that's acting upwards, we'll say that it's the force applied the ceiling on A. Okay, so that's the ceiling acting on A. Now we also have a string acting downwards from A connecting to B. So we would say that that is the force of B on A, partly because if you think about what's applying that force on A, and it's the fact that there is a mass B. Okay, so we have two forces here, and we don't want to forget the fact that since the sphere has mass, it's going to be interacting with Earth in the form of the force of gravity. Okay, so we also have a downward force, and we'll call it Fg, and I'll use the subscript A to represent that. That's the force of gravity acting on A. Okay, so this would be the free body diagram for sphere A. We can continue this idea and draw for B. So I'll draw FBD of sphere B. I'll draw in this one as well. Boom. Okay, sphere B, and same idea. We have the force of gravity acting down on sphere B because it has mass. We also know that there is a thread acting upwards on B, and that would be the force of A acting on B. And we have a thread acting downwards between mass B and C, which would be the force that C is applying on B. Okay, so there's our free body diagram for sphere B. And last one here is we want to do a free body diagram. I'll do it over here on the right. Free body diagram of sphere C. I'll draw my box to represent sphere C. And we say that if you look at the diagram here, we have a single thread acting upwards on mass C, or sphere C, which we're going to say is the force of B pulling on sphere C. And now there is no downwards threads acting on C, so the only downward force here would be the force of gravity acting on C. Now I just need to fix my C there. There we go. And these would be our free body diagrams of each of the spheres. So you can see that each of them have at least two forces acting on them. Some of them have what I would call Newton's third law pairs, or action-reaction pairs, that we have, say, force of B acting on A, but we also have the force of A acting on B. So that would be our action-reaction pairs right there. We have force C acting on B, and we also have the force of B acting on C. So that would be another action-reaction pair right here inside this example. So B part of this question asks us to find the magnitude of the tension between sphere A and B. So that's this rope right here. Okay, so that shows up either as this force right here or this force right here, because they are both action-reaction pairs, and we know that the magnitude of them is the exact same. They're just acting in opposite directions. Okay, so I'm going to work with free body diagram for sphere B, but there's a few things I don't know. I know that I was given the force of gravity acting on B, and that was our 15 newtons given to us in the question. However, I don't know the magnitude of force of C on B. So that's going to force me to use this third diagram, free body diagram, to find that force of B acting on C, which will relate to my free body diagram for sphere B. Okay, so we're going to start in on that last free body diagram. So I'm going to say start with FBD on sphere C, or of sphere C. Okay, so if we look at the forces acting there, we can say that the net force in the y direction will be equal to the mass of sphere C with an acceleration, and we'll say that that's an acceleration in the y direction, and the force is a vector, so is the acceleration. And since this object is not accelerating, this term here will actually go to 0. We can say that that acceleration is in fact 0. So this has Newton's first law built into it, that unless there's a net force acting on the system, it's going to stay at rest or stay in constant motion. So here we have the net force acting on sphere C. I'm going to say FB on C, and that's acting upwards for my free body diagram, plus there's going to be the force of gravity acting on C, and we said that that was downwards from our free body diagram, is equal to 0. All right, so I can actually substitute in the fact that I know that the force of gravity acting on C is 11 newtons, which was given to me in the question. So I can say that FB on C acting upwards plus 11 newtons acting downwards is equal to 0. So let's, downwards. Let's make sure that our forces are actually acting in the same direction. So I have B on C acting upwards minus 11 newtons acting upwards is equal to 0. So now that we know both of our forces are pointing in the same direction, I can drop the directions, and I can say FB on C is equal to 11 newtons from rearranging my equation here. And so therefore, FB on C as a vector is equal to 11 newtons, and we said that was upwards. Now, does that make sense? We drew in our free body diagram that yes, it was in fact acting upwards. And I'm going to use this information, again, using Newton's third law, that the force of B on C is going to be same in magnitude but the opposite direction as the force of C on B. So, since Newton's third law, FB on C is equal to the negative vector of C on B as a vector. So that means that we knew this from above, 11 newtons up is equal to negative FC on B, which means that 11 newtons down is equal to FC on B. Okay, so I'm just going to insert another page into my document here. Page manipulations, insert. I'm going to insert a page here, and we can continue away with this. Okay, so looking back at our free body diagram, we were given this information about the force of gravity on sphere B. We just calculated the force of C applied on B, and the only thing left for us is this force of A on B, what we were asked to find in the question. Okay, so I'm going to say using free body diagram of sphere B, the net force in the y direction is equal to the mass of sphere B multiplied by the acceleration of that sphere. Notice that because I'm using the free body diagram of just sphere B, I'm using just the mass of that object. So again, since the object is not accelerating, this term on the right hand side essentially goes to 0, and we have Newton's first law. And then that allows us to say that the net force in the y direction, Fa on B, and we said that was acting upwards, plus another force, so we said the force of gravity acting on B, and we said that was downwards, plus another force, which we said was, just want to get my directions right, C on B, and we said that was downwards from our free body diagram, is equal to 0. And we do know these values. F of A on B is upwards. The force of gravity on object B is 15 newtons. 15 newtons, and that's acting downwards. Plus, we just found above 11 newtons acting downwards was the interaction or the tension force between spheres C and B. So we have the force of A acting on B, and we said it was upwards, will be equal to minus negative 15 newtons acting upwards, minus 11 newtons acting upwards is equal to 0. Now all of our vectors are pointing in the same direction, so we can just drop the directions for now. Fa on B, subtract, this will be 26 newtons, is equal to 0, which means that Fa on B is equal to 26 newtons. And we said that it has to be upwards, so therefore Fa on B as a vector is equal to 26 newtons acting upwards. Now, the question actually asks us to find the tension between these two boxes. This would be the tension acting on the rope or the thread between the two of them. So the tension in the thread between sphere A and B is 26 newtons. Now, I'm going to only identify it as a magnitude simply because if we think about our free body diagrams, for A acting on B, it's directed upwards, but for B acting on A, it's downwards. And these are the same magnitude, but just, again, different directions. Okay, so that's the solution to problem number 1. I will make another video for the solution to problem number 2.